op-amp circuits and what all things we can do using op-amp. Okay, up till now we have seen 3 different labs exercises like basic electronics, digital electronics, and your advanced electronics. So if there are any doubts from any of those, just let me know. So otherwise, we can move on and start with today's session. Are there any other are there any doubts from any of the last sessions?
Sir, good morning, sir.
Sir,
Good
I
morning,
have
sir.
simulated Class A amplifier. That was assignment of last session.
Okay.
Will you please check, sir? I am not
Yeah.
sure it is correct or not.
Sure. Show me now.
Sir, for the buzzer, whether we get to put the frequency also.
No, I didn't get you, sir.
Sir,
Sir, is my screen visible, sir?
Yes, ma'am. Your screen is visible.
So this is Class A amplifier. That was assignment number 3. So
Yes,
I
ma'am.
have done this AC sweep. Sir, is it correct, sir?
Yes, circuit looks correct. Only thing you can add few more elements like your resistance and capacitance, which will increase your gain. Right now you can see that the solid blue line is way below than the solid green line. That means
Yes, sir.
we are not having any amplification here. The
Yes.
signal is already attenuated a lot. So we can you can add more elements which will increase your gain. So, but the circuit is okay. You can assign more like resistance from your emitter to the ground and parallel capacitor there.
Yes,
And I
sir.
guess one resistance from base also can go to the ground. Then you can play
One
around with the value
resistance from this, sir?
to the ground. Yeah.
Okay.
So this you can try out.
Okay.
And you can play around with the values to see which value is particularly giving you the maximum gain bandwidth. And you can use that like I showed you yesterday, because either you do calculation for this particular circuit and find out all the values that will give you the best gain and bandwidth, or otherwise you can just play around and see where you're getting these values, because this AC sweep is actually coming in very handy in this thing.
Yes.
You can just change the value and run the AC sweep and see if you're getting a good bandwidth and gain also.
Right.
Okay.
Yes.
Okay.
Thank you.
So, okay, sure. I guess there was one more query.
so if we want to connect buzzer,
okay,
we got to set the frequency also. So as you said,
yes, sir.
Told that instead of speaker, I connect the buzzer.
No problem, sir.
So
you can connect anything. As I said yesterday, that we just have to connect one load there. It doesn't have to be specifically a buzzer or your resistance. It can be anything that you want. But most basic thing that people use is the resistance. So that also you can use. That is up to you, sir. But buzzer can also be used. No problem in that.
Actually, I connect buzzer.
Yeah. You can connect buzzer.
Okay.
So any more questions from any of the last session? Okay, so if there are no questions, I will move forward with our today's session. Okay, I hope my screen is visible.
Yes, sir, it is visible, sir.
Okay, so we will look at our day 4, which is on op-amp lab. Okay, and in op-amp we have some particular sort of circuits which are very famous. Now op-amp itself is an amplifier chip, or you can say. Okay, and it is actually being used in most of the in many applications. So the applications are enormous for this particular op-amp. That is why it is a separate subject in ECE. Otherwise it could have come under normal amplifiers and all, but it is a separate subject by itself, because the application base that it offers is a lot. Okay, so this is what it looks like, the symbol, and the IC. The most common IC is your LM741. Okay, but yes, obviously there are multiple more ICs that you can use depending upon the specification of your application, like input voltage current or output voltage current that you need. All these things will help you select the particular part number. Okay, but in our labs we use 741 commonly. Okay, then op-amp, as you see, it's a chip here. Okay, so obviously it has multiple stages inside it, so we can categorize it in 4 different stages. One is your input stage, or you can call it dual input balanced output differential amplifier. Now differential amplifiers are again a type of amplifier that we can implement using our normal NPN transistor. Okay, that also I'll show you just in the next slide. Then we have another stage which is called intermediate stage, and this is again a differential amplifier only. Okay, then there is a level shifting stage. Okay, so then the last one is your push pull amplifier, or you can say output stage, which will increase the impedance for the output so that you can get a better impedance matching. Now this is what our differential amplifier would look like. So as you can see, it is a common emitter configuration what we're using here. Okay, so two common emitter circuits are what we are using here to make one differential amplifier. Okay, and in this case, the output that we measure is between these 2 points, not with the ground. Okay, so which basically increase our signal to noise ratio also, because many times ground is a source of our noise also, which is eliminated here. So there are multiple other benefits also. I'll not go into all that. That is why this particular differential amplifier is being used in making this op-amp. Okay, then okay, so some of the applications, as you can see here, we will try to cover a few of them. Okay, and but anyway, op-amp circuits are pretty easy to use, so you can work it out on your own, also the remaining circuits. Okay, first circuit, or very common circuit, is our inverting amplifier. So in inverting amplifier, basically it will amplify your input as well as give it a 180-degree phase difference. Okay, so let us just try to implement, and as you can see, the circuit is pretty similar: one op-amp chip, 2 resistors only. Okay, then obviously to enhance your output you can apply multiple other components also, but this is the most basic circuit that can help you achieve your task. Okay, so again I'll just go to my multisim live profile. Okay, I can go under circuit and check out my previous circuit, or just directly open this create circuit here. Okay, so once you create, you will reach here. Okay, this, which is our breadboard, as we have been working over it from last 3 days. Now if you see on this left hand side all the libraries that we have, so under this amplifier you see we have this op-amp symbol is anyway here. So we have 3 input op-amp, 3 terminal op-amp, 5 terminal, then an idle comparator 555, and then we have a specific op-amp IC also, like LM324 or UA741 IC is also there, which will have all the spice model for this part number, and you can use those. But I'm going to use the generic one, and I'll be using 5 terminal op-amp. Okay, the difference between 5 and 4 terminal is that obviously the number of terminals. Here we have plus VCC and minus VCC, and I can give any particular supply here. Let's say if I select 3 terminal op-amp, we don't have that here. Okay, so that is so you can see the specs here, and you can see it has given plus 12 to minus 12 here. Okay, so this is by default the default value. You can change it to, let's say, 15 or 10 or whatever you want, but in circuit you won't be able to connect it. So we personally are trying to achieve a set We personally are trying to achieve a system where we can give a feel of a real lab. So that is why we are not going to use this one, because in this case, in our lab case, we always apply supply to our VCC and minus VCC here. So that is what we'll be using. That is why we'll be sticking to this 5 terminal op-amp. Okay. So in op-amp IC there are I guess 8, yeah, 8 pins, and we don't use all of them. So these are the 5 pins basically what we use. Okay, so let us just try to implement this circuit. We will have two resistors, R2 and R1, and the gain in this case would be minus R2 over R1 into V in. This would be our V out, sorry. Okay, so this is what we'll do. Let us just try to connect. Okay, so this is my, let's say, R1, and then I'll have R2. Okay, then I will have one AC input, and then obviously I will also take a DC volt DC supply for my biasing. Okay, so let me just copy this for my other side. Then I will have ground signal. Okay, here we don't need, and here let me just put it here. Okay, so let me just first connect it here. Okay, so let me give this 15 volt, and it's also 15. So you can see that I have connected the negative end here, okay, because this will give this minus 15. So plus 15 to minus 15 is what we have given here. Then this. Okay, so I will need one more resistance for my load, which will act as my load. Okay, so let us just connect this also, and this one will go to this. And this here is going here. Okay, and again this I will put in to the ground. Okay, so let me just put the probes now. So this is my output input, and this is my output. Let us just run and see if we are getting the value. Yes. So you see we have 180-degree phase difference, so it has been negative. 1 second, let me just give it. So you can see the input and the output are out of phase. Okay, so it is negative. Okay, so the inversion has been done here. So the signals are right now equal, because as I said, that gain would be minus R2 over R1. Okay, so this is 1 and 1, so that is why the gain is 1. So if let's say I increase it to 10, now what would happen? You see that the it has been increased. Now you see it is 10 volts, and this one is 1 volt. So the 10 difference is there. Gain is 10 in this case. So if I increase this, you see the gain has been decreased. If I make it 5K, so this should be now 5. No, what is this? This is your 1, and then this is your 2. Okay, yeah. So 10 by 5 is 2. So now it is 2. If I make it 2, then it would be 5. Okay, you can see that. So it is out of phase and we have a gain. So as simple as that, we can say. So this is a basic inverting amplifier. Any doubts on this?
No, sir.
Okay, so you guys can also try and make it. This is a very simple circuit. It will take a minute only. Are you trying? If you have any doubt, let me know. I'll give you 2 minutes to implement this circuit. If there are any doubts, please let me know. So I will run the AC sweep also to see if we have a particular bandwidth. Okay, now here if you see, my output is initially high. Okay, the green one is my input. Let me just. Okay, so the green one is my input. Okay, and the blue one is my output. So you see it is already above my signal. That means amplified. But after this point, which is like 3.16 megahertz, it will start decreasing. Okay, and after this point, which is my 80 megahertz, it will be less than my input. So that also we can check. So this is basically the bandwidth. The bandwidth is somewhere around here. So till 19 or 20 megahertz, this circuit will work properly. Otherwise, it will start decreasing. Okay, so let me just try that. Okay, so let me first see. Okay, so after 3 megahertz, it will start decreasing, and after 80 megahertz, it will be less than my input. Let us just try to give this frequency. As you can see, it is high right now. So we have given 1 mega. Now you see the signal is less now. Green one is bigger. Okay, let me just. So if I start decreasing, you see, if I'm decreasing it, the signal is increasing. But as I increase the frequency, signal decreases. And now you can see that it is obviously less than my input signal. So that is what we were trying to understand, the bandwidth of our signal. Now one more question I have for you guys. I have given one sine wave, but here I am getting in output a square wave. Can anyone tell why? Okay. So you see this is a sorry triangular wave. Can you see why?
Sir,
Yes, ma'am.
I guess for low frequency range, it is acting as a differentiator.
Mm,
This sine wave is getting differentiated and converting into this
From you,
triangle wave for
no,
low
it is not that way.
frequency.
When it is differentiated, then also it becomes sine wave. If you differentiate, then also become a cos wave like that. I think
Okay.
because of the
so,
feedback, the 15 volt, that is
because of
output,
feedback, yes,
that is output, it is oscillate between only plus or minus 15, like that.
exact. Yes, sir.
Okay.
Okay, so are you all done with your exercise?
So 1 minute, I'm doing. Yes, sir, I have done now.
Okay, so anyone having any doubt on this? Okay, so if there are no doubts, let us just move forward. Okay, so the next circuit is our non-inverting amplifier. Okay, which also works on similar principle. Okay, so this is the circuit that we are going to use here. This one we will ground, and then we will have 1 second. I guess the circuit is not correct here. Okay, yeah, circuit. I think this should be minus and this should be plus. Okay, so yes, the circuit is not correct. So anyway, we'll try to make it. Let me just name it op amp lab. Okay, and stop it. Then I'll delete this part. Okay, and again I will take a 5 terminal circuit. Then again we will need 3 resistance here, then 1 input. Okay, and then we will need DC supply here. Okay, then we will need some grounds. In last case, what we did connect our input here. In this case, we will be connecting it here. Okay, and then my output would be between second here and here. So this one will also come to ground. Okay, and this here will also come to ground. Okay, then this one will come here. Okay, so let us give 12 volt this time, and this also has 12 volt. Okay, so gain in this case would be 1 plus R2 over R1 divided into multiplied by this 1. Okay, so this is how it should look. Let us just run this. Oh, sorry, I forgot to add probes. So one probe at the input, then another here at the output. So let us just now run this and watch our graph. Okay, so let us just fit it on the graph. Okay, so this one again is getting inverted.
Sir, this feedback resistance should be on negative side only.
Okay, that
R2.
this you're saying should be here.
Yes, sir.
Okay, that is what maybe I missed. Uh,
So normally we will get in. So
uh,
normally we will get only the inverted waveform only will get up and
no, no. In so we are trying to implement non-inverted amplifier, na. So
yes,
in
yes,
Can
this
I
yes.
case,
share, sir? Hello, sir.
yes, sir.
Can I share for you?
What? Yeah, sure, sure. 1 second, sir. Let us just try this one.
No issues. Okay.
Okay, now we have the same thing. Yeah,
Yeah, fine, sir.
this one is fine. So anyway, it is cut off. Let us just increase the resistance here. So this is acting as a comparator, I guess. Okay. Okay, so these two are actually same only. What are we missing then? Oh, 1 second. One more thing. No, this. No, again, this is wrong. Okay, so they are same right now. Let us just try and. Okay, no, this one also wrong. Yes, sir. You were saying something?
Pardon, sir?
You were saying something, sir.
No, I didn't say anything, sir. If you want, I can. If you want to share, I can share the circuit. So that's what I'm.
Oh, that also we can do.
Yeah, fine.
Nice.
So in non-inverting, plus is grounded and minus is connected with two resistors.
plus is grounded.
Hello, sir. Hello.
Yes,
Hi,
sir.
this is
So sorry for interruption.
Yeah, tell me, sir.
So same like inverting, sir. Okay. You just interchange the input and ground, sir. Okay. That's
input
it.
and ground, sir. Sir.
Actually, inverting, you are going to give the input for the inverting terminal. Non-inverting is grounded. You just swap those things. So that's it enough. Okay.
Okay.
Same like as inverting, sir.
Plus is minus, minus is should be plus here.
So what you're saying is that my input will directly come here.
Yeah, from 3 to directly input, sir. Fine.
Yes, sir.
So from negative to 1 kilo ohm and feedback
One
also.
and
Yeah, fine.
feedback resistor, and one
Yes.
is 1 kilo ohm with one terminal grounded.
So can you
Another
check?
two,
Uh,
yes, sir. Connected to three.
that's all, sir.
Yes. अब आएगा.
Okay. Okay, 1 second. We forgot our probe here. Okay, now we have that. So thanks for the help, ma'am and sir. So yes, you can see that we have some amplification. Let me just make it 1 volt. Now in this case, the gain is 1 plus R2 over R1, so which is 1. So 1 plus 1, 2. So that means the gain factor is 2 here, and the input is 1 volt, so the output is coming as 2 volt. And they're in phase, not out of phase. So if I increase this gain, let's say to 10, now it is 10 plus 1, 11. So it should be 11 now. So you see, it is 11. Okay, so this is what our inverting amplifier would look like. Okay, so any questions on this? So these are very common, as you can say, simple circuits. Okay, not much circuitry is required. Most of the things that are complicated are already inside the op-amp, which is the various stages that actually we were trying to achieve yesterday. Not all of them, but yes, something like that. The common emitter and all we were trying to do yesterday. So all these stages are inside it, and now we are just using one ready-made product here. Okay, and it behaves. So that is a benefit of using it. It's really simple to use and it gives you good results. Okay, so this one is done. Then our next circuit would be current to voltage converter. Okay, so now in this case you can see again the circuit is similar. On the inverting end we have our current input which will be converted to voltage. Okay, so some calculation for you, you can look at this calculation. So okay, so let me just implement this circuit. So we have this here. Okay, and this one will go to ground. Okay, then apart from our input, we have a AC current source. Okay, so we have a current source here, not the voltage source. So this current will be converted to the voltage. Okay, so we will, let's say, start with 1 milliampere current here at a frequency of 1 kilohertz. So one second, this is a voltage probe. Now I need a current probe here. So this is a current probe, and again we have the circuit remains similar. Yeah. So in this case, V in will be equal to minus of V naught upon R. Only the single resistance that we are using here. Okay. So our output is I in into RF. So again, it is like Ohm's law only. Okay. So let me just run it. Okay. So right now we have 1 milli. and 10K. So you can see that the output is 10. That is what we are seeing now. Like if you see here, V naught is equals to minus of V in into RF. Okay, our V in is 1 milliamp and RF is 10K. So if you multiply them, so 10 into 10 to the power 3 into 10 to the power minus 3, which will cancel out. So only 10 will remain, and we will have minus of 10 volt. That minus represents phase shift, which we can see here. This green one is our current dotted one, and our voltage is out of phase, and it is 10 volts. Yes, okay. And this side here is the current axis. This is the voltage axis. This is the current axis. You can see. So the current is 1 milliamp here. Yes. Okay. So this is what we are getting if we try to increase the voltage. You see, we are actually surpassing our cutoff, so that is why it is converting to square wave here. We decrease it, so 4 into this, so we are getting 4 volts. Okay, so this is how this simple current to voltage converter works. This is again a very simple circuit. So any further question on this? So generally in op-amp lab, we basically put in we basically plot these graphs and record the gain of our output only. So not much analysis is actually required here. Only thing is what input we give and what gain we have given on the circuit, like what resistance. Then we try to verify with the practical results on what we are getting. So that is what I am also trying to do here, like calculating what we have given here and what should be the gain, and accordingly checking here on what we are getting. Okay, so again, let us run some AC sweep on this also to see if there is any issue. So if you see, this is my 1 second, please let me delete. Okay, so this is my output input current, and this is my output. So you can see that till this particular voltage, sorry, frequency, it is constant around 12.5 megahertz. After that, it starts decreasing. So the bandwidth for this system is around 13K, 13 megahertz. Sorry. Okay, so after 13, the output will start decreasing. So let us just try to see that also once. Because again, bandwidths are important in these circuits. Let me just make it 10. Okay, so we have a 10 volt input here. Sorry, output. So let me just increase it. So after 12, around 11, 12 mega, it should start decreasing, as you can see here. So we will be going towards. Let me just. So as you can see, it has already started decreasing. Okay. It's still decreasing, you can see. Okay, so we are at 1 mega here, and now it is still decreasing also. Okay, so this is what the bandwidth we can check here. What bandwidth we are working in. You can see the signal has changed a lot. It has even changed the shape also. It is sort of triangular wave now. Okay, so this AC sweep also we can test here. Okay. And even actually this AC sweep also shows us about phase also, like what phase changes in phase will happen with the frequency. So that also you can see here. Okay. So now we will move toward our next circuit, which would be a basic comparator circuit. Okay, so comparator circuits are used to compare two different waveforms. Okay. As you can see in here, so if I give a sine wave on one input and I give another reference voltage at some particular wave, some at this another pin. So it will compare. So as soon as the sine wave crosses this particular reference voltage, it will generate a square wave. Okay, so that is what we are trying to see. So that is a comparator. So if it crosses any of the reference voltage that I have given, then there would be a change in the square wave. So we can do it in multiple way. Like I can give a single DC voltage here to compare, and a sine wave here. And I can give, let's say, both sine with different amplitude and frequency, or some difference like square wave or some triangular wave, and we can see all the patterns that we get. Okay, so let us just try. And obviously here we are not giving the feedback resistance, so our gain is infinite here. Okay, so obviously we'll not get infinite, we'll get clip off at our frequency, sorry, at our voltage, such which will be plus Vs to minus Vs. This is what we will be clipped off. Okay, so let me just delete this and this, and current source also will not need now. This probe also is not required. Second, okay, so this is my output, and I will connect a probe here. Okay, so you see I've given plus 12 to minus 12 here. Now let me just take one, let's say a square, sorry, a triangle. This is our normal sine wave. Then let me connect it to this. Okay, so I will give a reference voltage using a DC supply only. Okay, so this would be here, and the other end will obviously go to ground. Okay, now this reference voltage, let me make 1 volt. Okay, and this let me make 2.5 volt. 2.5 volt. And the frequency, let me change it to 10 hertz. Okay, so now I will apply my 1 voltage input probe here and another here. Okay, running SSD. As you can see here, as soon as our input voltage is crossing this particular uh, reference voltage, which is set at 1 volt, we are getting a negative peak on our square wave. Otherwise, it is positive. Okay, that is because we are using the inverting end. Okay, so if let me just try to shift this to, let's say, 2 volt, and then you see now our negative peak is only for this time period. Okay, so I can just try to simply move it around and see it change. Like right now, you can see my input voltage is less than the reference voltage, so that is why it's a constant at 12 volt. Okay, and we are not seeing anything, any downward peaks. So if I increase it a little, you see I'm starting getting some negative peak now. I can reduce it, you see here, and then I can try to increase it further. Okay, so this is I am doing using my input. So this is plus 5 volt. Let me just increase or decrease this reference voltage. Okay, so if I give it 0, you see that it is giving perfect square wave with 50% duty cycle. Okay, so because the complete positive cycle of this sine wave is over our reference voltage. So that is what we are getting here. So now let me just stop and add, let's say, something else, a triangular voltage instead of our DC reference voltage. So DC was pretty simple to understand. Now we will try to see the same thing here. How this is. Okay, so now this end will go to ground. So this is again the voltage. Let me just decrease it to 500 millivolts. And this curve will come here. That is just from this. So what is here? Lifetime must be greater than or equal to 0. Okay, so we are not able to see anything here. Let me just expand it. So you see here we are getting, as soon as these voltages are crossing, you can see there is a peak. You can see here also. So let us try to increase the voltage here. So the voltage that we have given here is 1 volt, and here we have 5 volts. So this is, oops, I cannot give a lesser second. Okay, so let me just try to increase this voltage. Let's see. Okay, now you can see in this case, this will give some result to us. The same thing that we were trying to understand earlier, we are getting now. Okay, so let me just freeze it on a simple thing now. Here you can see, now our reference voltage is a triangular wave. So as soon as our input voltage will cross it, it should give us a downward peak. So here you see, first thing, when it crosses it, we got a downward peak here, and obviously you can, there's a difference here because there's a fall time which will be incorporated here. So as soon as it gets below our reference point, it will go back to positive again. Here also the same thing has happened. You can see, and this particular point you should see. Like at this point, it crossed, so it came here, came down, and at this point, it again went below our reference, and it again went up. So this is a bit complex than what we were seeing up till now, because the DC was a straight line. and it was pretty easy to understand. But in this case, our reference is also fluctuating. So this is what we can see. Okay, so if let's say I replace this particular source with something else like a square wave, what would happen in this case? Let us see. So 10K and 1K. So let me decrease this frequency there. And okay, so you can see here, in this case, it went up and we got a negative. But on the same hand, this also went up. So there's only a peak, a sharp peak here. Okay, otherwise it is always up. Let us just try to see if we can change some values. If I change frequency, let's say, now you can see some peaks. So now this is something interesting we can look at. Now at this particular point, our input signal is greater than the reference, and you can see a peak, a downward peak here. And at this point here, this is a transition point. So here our actually the level was this initially, and our input voltage crossed it. So that is why it came up, but at the same time, this also went up, and that is why this again went back to the positive state. So that is why there is a small peak here. So you will see this transition on all the positive peaks. Why not on the negative peak? Can anyone tell why do we have these spikes on the positive edge, not on the negative edge? Can anyone tell why? Anyone? Any guess why? It's not an exam. Why we are getting this peak at positive end only? Why not on negative end?
Less than input is less than 90 voltage.
Like
Exactly.
positive peak or something.
So the voltage at positive end is less than the negative.
What's it? So I guess I was trying to say that in this case, if you see, the reference voltage is this 0 volt, and our input is less than that. So as
Yes.
it reaches this point, it knows that it is going over 0 now. So the peak will come down. But on the same hand, this also went up. Okay, so the peak again went up. But if you see now, the reference voltage here is 4.6 volts. Okay, and our signal is already less than that, so it will keep on remaining on the positive side of our saturation. So there is no transition on this point. Actually, there was a transition because our input was crossing, our input was going over the reference voltage, but in this case our input is not going over the reference voltage. That is why there is no peak at this end. Okay, so this is one thing. Okay, so any doubts on this? Are there any doubts? If not, we can stop for a break.
Yes, sir.
Okay, so we'll meet again at 12 and we'll continue with the other op-amp circuits. We have some other filters and everything also aligned in next session.
Okay.
Okay, so we'll start at 12.
Right, sir.
Okay.
Thank you, sir.
Thank you.
Ma'am, attendance.
Yes, I'm posting the link. Just a minute.